Hi everyone, this is Qingyun. I was a math PhD at Stanford University, and this is a joint work with Kenji, who is a postdoc at Harvard University. Our work will present you a recipe for global convergence guarantee in deep neural networks. As a mathematician working with deep learning, there are three major mysteries. First is optimization. Second is representation. The third is generalization. In this talk, I mostly focus on optimization perspective and touch a little bit on representation and the generalization perspective. About optimization, it's about a global convergence guarantee for the how can we get our parameter W in this example to be the global optimal for a given loss function. Training DeepNet is a hard problem because it's a non-convex optimization problem as a variable of W. And algorithms like SGD don't provide global convergence guarantee. Because if you initialize at different place on this landscape, you would converge to either a saddle point or local mean or a global mean. And if you go to a saddle point with the noise, you might be able to escape and eventually go to either a suboptimal local mean or global mean. And without global information, you are not able to tell whether you arrived a global mean or a local mean. So the pursuit of this work is to find a training algorithm with a theoretical guarantee of global convergence for a class of neural net problem with good enough landscape. How can we get a better landscape and get a decent optimization guarantee? In the past research, people discovered that overparameterization helps optimization. What is overparameterization? In a naive term, if we think about a fully connected net, as we showed before, if we make all the hidden layers extremely wide, even wider than the number of data points, like say polynomial to the number of data points, then there would be guarantee for global convergence. What's the intuition for overparameterization? Professor Andrea Monari from Stanford have this great ketone. It explains that neural net with the ability to arrive zero training error are interpolators. They interpolate the entire training data set to have zero training error. And among all such interpolators, SGD successfully find a minimal norm solution in some abstract sense so that you can have a regularized function that also generalizes. To capture the intuition for optimization perspective, people come up with a theory of neural tangent kernel, where neural tangent kernel is defined as K in the following. We can think of neural net as a kernel machine with the following neural tangent kernel. With a so-called neural tangent kernel regime of training neural net, we can have a highly overparameterized net and use very small step size. In this case, the deep net can probably converge to global optimal. And if we want to simplify, we can think of NTK regime as the regime where this kernel don't change as a function of training time. So NTK regime for this extremely overparameterized net is capturing only part of the picture. As we're showing in this ketone, normal deep net in practice is like this real cat. It's cute and it has a corresponding kernel KT that is changing with time. We call this the effect of representation learning. The kernel and the corresponding features significantly change over time of training by adapting for the particular instance of training data. Kernels or features in this case are representations learned from data instead of handcrafted or fixed before training. On the other hand, if we look at this funny stretched cat, It represents extremely overparameterized deep net without representation learning. In overparameterization theory, kernels or features do not change much during training, so there is no significant effect of representation learning. In this regime, deep nets behave like a linear model with a fixed kernel, which enables theory because we already understand how to handle fixed kernel mathematically. But from the point of view of real-world deep networks, representation is a critical aspect. Without that, we are far from a satisfactory theory for deep learning. So natural question is it possible to have global convergence guarantee for training deep nets that allow representation learning? If we think from first principle, the question we should ask ourselves are, what elements are needed for the recipe with a global convergence guarantee? First, we need to find a good algorithm that satisfies the following three criteria. First, the algorithm is able to find the interpolators that have zero training error. Second, it should provide implicit regularization. Third, it should do representation learning. SGD on normal practical deep net training does implicit regularization, and it also does representation learning, but there is no guarantee of finding interpolators. To have such guarantee, we also need to characterize the classes of deep net architecture with enough capacity to interpolate the trained data. And in this talk, we give our recipe that follows this principle. First, in terms of algorithm, we come up with a two-phase modification to your favorite training algorithm like SGD or ADAM. Our modified algorithm would allow representation learning, but still inherent global convergence guarantee from NTK regime. Second part of recipe is a criteria to check, which is the expressive condition for a given architecture and dataset pair. It characterizes the capacity needed for the network to interpolate training dataset. First, let's talk about the two-phase modification of the algorithm. Let's take your favorite first-order stochastic training algorithm, or even non-stochastic algorithm like a gradient descent. First, you can convert it into a two-phase algorithm, where phase one, you do exactly what you do before. You do representation learning. Let's say originally you have SGD with 100 epoch. Now you cut the 100 epoch into 60 epoch and 40 epoch, where you do the first phase in the first 60 epoch, and then you go to the second phase. In the second phase, you do a random perturbation to add Gaussian noise on all but the last layer weights. Then you perform so-called rank preserving lazy training. It is a generalization of the previous NTK regime training, where you need to choose a small enough learning rate so that you guarantee the rank of NTK do not decrease over time. So this is a more relaxed condition that includes the NTK training where it practically don't change the kernel. And a special case of this is if you fix all the rest of layers and only train the last layer in the second phase. This is our specific algorithm, and you can go to our paper or our poster for more detail. So the next question we need to answer is, how much capacity do the deep net needed to interpolate a given training data set? We're calling this name expressivity condition to guarantee global convergence for our proposed modified training. We can do a check of this condition before the training start by taking a given data set and choose a network architecture and say if there exists a choice of parameter that can interpolate all the training data in the sense that the rank of the last hidden layer output is full rank, equal to the number of data points. Or we can look at the determinant of the linear space spanned by the last hidden layer H and the bias 1. This condition is a dataset and architecture dependent condition, but it is independent of training time, so you can check this prior to training via numerical linear algebra. Practically, you can just sample a weight and check whether it satisfies this full rank condition. With this expressivity condition and the two-phase modification algorithm, we have the following theorem. Informally, admitting some mild assumptions that would actually hold in real neural net training. A real condition that under expressivity condition, and if we use a modified stochastic training algorithm, then the algorithm would converge to global optimal with a rate of 1 over square root of t. There are two versions of our theorem. First, it's about fix all but last layer weights and train the last layer weights in the second phase. The second is about the general rank preserving lazy training for all layers. We can say in both cases, the convergence rate is 1 over square root of t. And what are the examples of expressivity condition? Our first example that we are able to prove is a fully connected net with a wide last hidden layer. So mathematically, we are able to show that for all data sets, a fully connected net with a wide last hidden layer satisfy expressivity condition if the hidden layer dimension is bigger than or equal to the training data size. As shown in our example, we need all the other hidden layers to be as wide as the input dimension, but we need the last hidden layer to be as wide as the training data set dimension. We are able to also numerically verify expressivity condition for ResNet with the extra wide fully connected layer. By numerically check, I mean, for a given data set like CFAR 10, we can randomly sample a single weight and check this randomly single weight vector whether it satisfies the expressivity condition, which is a full rank condition, stating that the span of the last hidden layer H and 1 is having the rank of the number of training data size. For ResNet with the extra wide last layer, we can say if we train with the base algorithm SGD, we have the blue curve of training trajectory. And if we train with our modified algorithm based on SGD, we have this red curve, where in the first part, it follows the exact same statistical trajectory. And there is a clear transition between first phase and second phase, where with the random initialization and this rank preserving lazy training, we can say the second phase trajectory steadily goes to 0 for both CFAR 10 and the SVHN. Empirically, we are able to show that for the following 4 datasets, MNIST, CFAR 10, CFAR 100, and SVHN, we are able to check its expressivity condition numerically. And then a natural question is, what about test error? What about generalization? So we also look at the test error for each data set for both the data augmentation case and the non-data augmentation case. We can see in all these examples, our modified algorithm has slightly better error than the original base algorithm. Of course, we don't have a theory yet about the generalization perspective. And we also check the stability for different choice of hyperparameters. So in our modified algorithm, there's two hyperparameters. One is the fraction of transition time. The other is the noise standard deviation. We can say from the following table, if we choose 60% of the original training epoch to be the phase 1 and the rest 40% to be phase 2, and choose the noise standard deviation 10 to the minus 3, then we get the smallest test error for this special case of data set. In summary, in this work, we provide a global convergence guarantee for neural networks that are expressive enough to interpolate training data. So we have a good algorithm inspired by theory. So the next question is, can we actually finish the loop and think in practice, what are the special properties of natural data set that allows real world practical neural nets to behave so well? And looking into the future, for concrete next question, we want to ask, is there an algorithm with global convergence guarantee for optimization and also provably improve generalization? And furthermore, for adversarial training, would it also provably improve robustness? With all the questions, I want to thank you for listening to our talk, and please come to our poster section if you have time.